All right, guys, let's do the notes here in section 8 about the pH of weak acids and bases. This is straight up equilibrium. That's why we did all that icebox stuff in the last unit. So remember, the definition of a weak acid or base is one that does not dissociate completely in water. And so if you have a strong acid or strong base, then all of the ions separate out. We don't have an equilibrium because there's no back and forth. It's just forward to the products and done. But for the weak ones, then we've got some molecules still intact, whereas some of them have separated out. And so the big difference for us is, what is the impact on the concentration of H+. For a strong acid, concentration of the acid itself is the concentration of the H+, because it completely dissociates. But for a weak acid, the concentration of the acid itself is not equal to the concentration of the H+, because it exists in an equilibrium where it's going back and forth. So some of the acetic acid molecules dissociate into H+ and acetate, but some of them stick around. And so the question mark is, we don't know how much H+ there is at equilibrium. We can't say that we have a pH of 1 when you have a 0.1 molar solution of acetic acid, because you don't have a 0.1 molar solution of the H+ ion. Remember, pH is all about what the H+ ion is. So what do? We do icebox. Hi. This right here is, I think we've looked at it earlier this year. This is acetic acid. It just kind of shows you more of like the structure of the acid. So if we were to look at like a Lewis structure of this guy, it would look like this. And this is not in perspective. It's not Vesper, right? It's not the geometric, the molecular geometry or anything like that. But that's how the pattern of the bonds would go. And it is this hydrogen right here that can come off. None of these hydrogens would be considered acidic hydrogens, because the bond between the hydrogen and the carbon is not polar enough. The bond between this guy, these two guys, is polar enough that the hydrogen could come off, and then that O right there would have a negative charge on it, and we would actually see some resonance between these two guys right here. Sometimes the negative charge would be up there, sometimes it would be down here, and that double bond could go back and forth. Anyway, okay, so let's do this. So let's find what the pH of a 3 molar solution of acetic acid is. We are given the Ka because it's a weak acid. We write out the equation for dissociation. So we start with acetic acid. You can write it the way that you're used to. It's okay. In equilibrium with these two guys. And for the ice table here, we have an initial concentration of 3 molar and nothing for those guys. It goes down, it goes up, and up. All ones in the coefficients there. So at equilibrium, we have 3 minus x, x, and x. And we need to set this up in the equilibrium constant expression. Remember, you get products over reactants. And we have a number, 1.8 times 10 to the minus 5. And we have 2 x's and a 3 minus x. This will be a quad form situation. We'll end up with an x squared on top. So we need to multiply both sides by 3 minus x. Then we will distribute the 1.8 times 10 to the minus 5 inside. Let me find my calculator. Okay, when I distribute that inside, I got 5.4 times 10 to the minus 5 minus 1.8 times 10 to the minus 5x is equal to x squared. So when you do quadratic formula and bring everybody over to the same side, you end up with A is 1, B is 1.8 times 10 to the minus 5, and C is a negative 5.4 times 10 to the minus 5. Plug that in the calculator. All right, the positive value for x is 0.007339. And so now we can return that number to our equilibrium concentrations. And in previous unit, we would calculate all three of them, right? We would say, oh, this is what they all are at equilibrium. But frankly, the only one that we care about right now is the H+. And the H+ concentration is equal to X. And so it is 0.007339 molar. And that is what we would put into the negative log in order to find out what the pH of that is going to be. Notice how much smaller this value is than the starting concentration of the acid, right? This guy, this equilibrium favors the reactants, so we don't have very much products. We don't have very much H+ and acetate ion. But we do have some, and so we need to calculate that pH now. And when I do that, I get 2.13 as the pH there. Okay, so this is how we would have to do for weak acids and also for weak bases, although it would be a little bit more complicated because for a weak base, you would be given the Kb and probably be using an icebox to find the OH- concentration. But then once you have the OH- concentration, you could do just like what we've been doing before. You could find the POH and then the pH, or you could get the H+ concentration using the Kw and then get pH, right? Either way would be fine. We typically stick to weak acid calculations, but of course you could certainly do this with a base and it would be very similar.